Welcome back. This will be a short video lecture on section 1.4, applications. Now, this section is short enough that I'm just going to do it in one installment. And really, I just want to show you two things. I want to show you a main idea, and then I want to show you how we can use this main idea in some examples. So let's talk about the main idea. And what I want us to do is to work a problem so the main idea is in some sense embedded in the solution to this problem. So let's take a look at this problem. Let u be a unit vector. I want to show that the component of the vector f in the direction of u is the length of f times the cosine of the angle between u and f. Now, in all of our applications, f is going to be a force vector in the plane. And in the plane, there are two standard unit vectors, E1 and E2. Now, what this main idea allows us to do is to take our force vector and quickly find the components of that force in the directions E1 and E2 simply by identifying the angle that that force vector makes with E1 and E2. So let's go to the document camera and work out the solution to this problem, and then we'll follow it up with a sequence of exercises that show us how to take this main idea and use it in various ways. All right, welcome back to the document camera. In this problem, we've got a unit vector u, we've got some vector f, and we know that the angle between these two is alpha. And what we want to do is investigate the component of f that's in the direction of u, and we want to show that it has a special form. Now, all of this discussion is predicated on u being a unit vector. So everything we talk about will change if this vector u is not a unit vector. So if we're working with something other than a unit vector, the first thing you should do is scale it back until it's a unit vector and then apply the things that we're going to talk about. So let's be careful to always address the situation with a unit vector. All right, now, the first thing we're going to do to try to make sense of the meaning of this is to look at the projection of f onto the vector u. So we can picture that it looks something like this in this case. This picture is not perfect, but it'll get the job done. So we're going to imagine stretching. In this case, we're going to have to stretch the vector u until we achieve the projection of f onto u. And so we know that this projection can be calculated quite easily, right? So this is the projection onto the vector u of the vector f, and that's going to be achieved by f dot u divided by u dot u in the direction of u. So we'll have, I should put arrows over all of these vector quantities. Okay? So this is the part that we want to focus on. This part here, because u is a unit vector, we can identify this as the component of f in the direction of u. Okay, so that's the component of f in the direction of u, and it takes on a pretty simple form here. It's just this ratio of these dot products. Now let's dig into this a little more, right? Let's dig in and see what we can do to simplify this a little bit. So let's work over here. So the first thing we can do to simplify this is to realize that u dot u is just the length of u squared. But u is a unit vector, and so this simply becomes 1. And now finally we can use our special formula for the dot product. We know that the dot product of f and u can be written as the length of f, the length of u, and the cosine of the angle is between them. In this case, that's alpha. But once again, this is a direction vector. So this is a pure unit vector. And so we can replace this by 1 and simply write length of f times the cosine of alpha. And so this is going to be our kind of recurring theme that runs through all the problems we're going to work in this section, is that when I want to resolve a vector f, typically in this section it's going to be a force vector. When I want to think of the component of the force vector that's in a given unit direction, I can simply calculate that by taking the magnitude of that force vector times the cosine of the angle between that vector and the prescribed unit direction vector. Okay, so this will be kind of our main tool of analysis as we progress through this section. Okay, let's head back to the course notes. Now let's work some examples. In this example, we have a force vector F pictured below. The magnitude of F is 5 newtons. Let's find the components of F in the directions of the standard unit vectors in the plane. So join me at the whiteboard for the solution to this problem. All right, welcome to the document camera. Let's take a look at this problem. Now, as we know, we've got a force of 5 newtons. There's a 20-degree angle here, and we want to resolve this vector into these two unit directions, E1 and E2, the standard unit vectors in the plane. Now, we know that what we need ultimately to carry out this calculation is we need to know what is the angle that this vector, and let's just call this, I'll label this vector F down here. What is the angle that this vector F makes with E1? Well, let's calculate that. We know that the total angle here is 180 degrees, and so it must take up the leftover bit. This must be 160 degrees. And the angle that this vector makes with E2 must be the 90 degrees plus the extra 20 degrees, or 110 degrees. And so we can simply write out the components as follows. So in the E1 direction, we have to compute the length of this vector. We're told that this is 5 newtons, so 5 times the cosine of 160 degrees. And when you carry out that calculation, you get something that's approximately a negative 4.7. Okay, and in the E2 direction, we're going to have 5. That's the magnitude of that force vector. And it's going to be times the cosine of 110 degrees. And when you carry out that calculation, again, you get something, this is an approximation, negative 1.7. All right, so those are the components of this force vector in these two standard unit directions. Now, if we wanted to recover the entire force vector, if we wanted to represent this force vector, we could paste these things back together again and say one way of thinking about F is that F is composed of a negative 4.7 newtons in the E1 direction plus, and again, this is approximate, negative 1.7 units in the E2 direction. So we could think of recovering this vector F as the sum of these components, these components that we found in the E1 and E2 directions. So that's a simple application of that general principle that we articulated in the previous calculation. So let's head back to the course slide. I'll show you a couple of other applications of this technique. Let's work a typical problem from an area of physics called statics. So the end of a heavy steel bar is being held off the ground by a cable that's attached to a wall. The tension in the cable has a magnitude of 200 newtons. Find the components of the tension in the cable in the directions of the standard unit vectors. How can we interpret the components of the tension? Let's go to the document camera and take a look at the solution to this problem. All right, welcome to the document camera. Let's take a look at the solution to this problem. And I think it helps to draw the situation over here just so we don't get confused by the meaning of this blue line here. This is denoting the cable, and we know that the force, the tension, is directed along that cable in this direction, but the length of this cable has nothing to do with the force vector per se. So this is, it's more helpful, I think, to go over here and kind of see what's going on in this fashion. So we've got our two unit vectors, standard unit vectors, E1 and E2, and there is some force vector that's being directed along this cable. Let's call that F. That's the tension in the cable. Now we know that it has a magnitude of 200 newtons, and we know that it makes an angle with the wall here of 38 degrees. And so because these are alternate interior angles, I know that that's also going to be 38 degrees here. So the angle that our force vector is making with E2 is known to us. That's that 38 degrees. And by adding on the 90 degrees, I know that it's making an angle of 128 degrees with E1. So in order to find the components of this force vector in the E1 and E2 directions, I simply have to carry out the calculations that we've been doing, right? I have to say in the E1 direction, the component is going to be the magnitude of the force, the 200 newtons, times the cosine of the angle between E1 and the force vector. Now that's going to be the 128 degrees. And when you carry out this calculation, you get a negative 123.1. Again, this is approximate. So it's going to be negative 123 newtons in that E1 direction. And the component in the E2 direction is going to be, again, the 200 newtons times the cosine of the 38 degrees. And again, that's going to be approximately 157.6. Okay, now this should look right. I mean, the picture we should get is when we resolve this force vector into these two components, the projection onto E1 is going to be pointing in this direction, and that corresponds to scaling E1 by a negative number. And when I project onto E2, I'm going to see a projection that looks about like this, and that conforms to scaling E2 by a positive number. So this conforms to what we'd expect from the picture that we're seeing. Now, what sense can we make out of these numbers? What meaning can we attach to these numbers? Well, one thing to think about is that this picture is representing a position that's in equilibrium. In other words, this is not moving, this is static. And so the forces have to be balancing each other out. And one way to think about what's going on is we have this F1, or this component in the E1 direction, is a negative 123.1. So we can kind of imagine that going in this direction. And that is opposing, that is in balance with, or in equilibrium with, the frictional force down here, which is keeping this foot in place, right? So there's a frictional force going in this direction that's perfectly balancing the tension in the wire that's going in this direction, that component of the tension in the wire. The other thing that's acting on this beam is gravity, which is trying to pull this beam down, and that's being opposed by this force, the tension, that component of the tension that's in the E2 direction. So those two are balancing each other out. So we've got the friction being balanced here by this component in the E1 direction, and we have the upwards pull on the tension, the part in the E2 direction, being balanced by the gravitational force, which is trying to pull this beam down. So that's the meaning that we can attach to these components. We can kind of reconcile them with the force of gravity and the frictional force. Okay, so let's head back to the class notes and we'll take a look at one more problem. Let's work one last problem together. 3 lines are tied together to a common ring and then roped off to separate trees. The system of ropes is under tension and in static equilibrium. If the magnitude of the tension in rope 1 is 100 newtons, find the magnitudes of the tensions in the other 2 ropes. So let's head over to the document camera and we'll see how our component analysis will allow us to answer this question. All right, welcome to the document camera. We're going to work through this problem and see if we can't find the magnitudes of all of the other tensions in the ropes. So we've got to find the magnitude of the tension in rope 2 and the magnitude of the tension in rope 3. And we're going to use the fact that the system is in equilibrium to help us do this. Now, just so we don't confuse the ropes with the forces, let's kind of redraw our picture so that we don't kind of get that confusion going. So we have some kind of situation like this. We've got tension in rope 1, tension in rope 2, and tension in rope 3. And these 3 vectors have to add to 0 because that's what it means to be in equilibrium. So fundamentally what's going on here is that F1 and F2 and F3 have to add up to the 0 vector. Okay, this is the condition of equilibrium. If the sum of these forces was not equal to 0, this thing would be moving in some direction in response to that unbalanced force. So the condition of equilibrium is that these forces add up to 0. Now, what we want to do is think about how we can resolve all of these components into the E1 and E2 directions. So let's just kind of give ourselves a little E1 and E2 here just for the sake of reference. So here are our basic unit vectors. There's E2 and there's E1. Now what I want to do is for each and every one of these force vectors is I want to express its components in the E1 direction and E2 directions. And one way to do that is just to kind of build a little chart here to kind of help us organize our work. So let's think about the E1 direction and the E2 direction. And we'll think about force vector 1, 2, and 3. Okay, so I want to express the component of F1 and E1 and E2 direction, same for F2 and the same for F3. Now we know that in all of these calculations, we have to first calculate the angles that these vectors are making with E1 and E2. So we'll make note of that angle and then we'll kind of do the calculation. Now F1 is the easiest. It's only in the E1 direction. It's all E1. And we know that it has a magnitude of 100. So it's easy. It's just going to be 100 in this direction and nothing in the E2 direction. Now what about F2? Now we don't know the magnitude of F2. So let's use this convention just to kind of help ourselves keep the math simple. Let's let little f2 stand for the length of that force vector 2. And we'll do the same thing. We'll let little f3 be the length of the force vector 3. That's going to save us some time writing all of this out. So little f2 and little f3 are going to stand for these unknown magnitudes. All right, now let's take a look at f2. From the point of view of f2, we have to figure out the angle that it's making with E1. Well, that's easy because that's already in the picture. That's 145 degrees. So I'm going to put 145 degrees there just to remind myself that that's what I need to work with. When I compute the cosine of that angle, I'm going to get a negative 0.82. So the contribution here is going to be a negative 0.82 f2, little f2. Okay? Now the angle here, I have to get the angle that F2 is making with E2. And here we can see that it has to be this excess. We can get up to 90 degrees here. So to get all the way to 145 degrees means that there's an excess of 55 degrees here that takes me to F2. So there's 55 degrees of angle between F2 and E2. So I have to work with that. When I compute the cosine of 55 degrees, I get 0.57. I'm rounding here just to kind of keep the numbers small. So 0.57 F2. When I look at F3, I first look at the angle that it's making with, or the angle between F3 and E1, and I can see that's in the diagram. That's the 135 degrees. And the cosine of 135 degrees is going to be a negative 0.71. And that has to get multiplied by the magnitude of F3. So let me write an F3 there. And then finally, I have to compute the angle that F3 makes with E2. So here I have to take that 55 degrees that I worked with earlier and this 80 degrees. Together, those will take me from F3 to E2. So that's another 135 degrees. And when I compute that cosine, it's the same as before. It's negative 0.71. And this is F3. Okay, so I've worked out all the components of the force vectors in E1 and E2. Now I have to return to my equilibrium principle. If the sum of these vectors is going to equal 0, that means the sum of these components in the E1 direction has to sum to 0, and the sum of the components in the E2 direction has to sum to 0. So this gives me two fundamental equations. The easier one is this second one here because it only involves these two terms. So let's write that one first. Our first fundamental equation that connects these these magnitudes together is 0.57 F2 minus 0.71 F3 equals 0. Our second fundamental equation is this one, which says 100 minus 0.82 F2 minus 0.71 F3 has to equal 0. Now let's use this one. We'll describe F2 in terms of F3 using this first equation. So this first equation would say that F2 is going to be 0.71 F3 divided by 0.57. Now when you do this calculation, you get something on the order of, again, these are all approximate, 1.25 F3. So F2 can be replaced by 1.25 F3. Now I'm going to go into the second equation and do that substitution. That also has to equal 0. Now, when you go through and do the multiplication and then bring these two terms together, you end up with a very simple equation that says 100 minus 1.74 F3 equals 0. And that says that F3 can be calculated as 100 divided by 1.74. And that gets you a number on the order of 57.47 newtons. Okay? Now, once we have F3, we can go back to this fundamental relationship that says F2 is the same as 1.25 F3. And so finally, we can calculate F2. I just have to take 1.25 times this calculated 57.47 newtons, and I'm going to get something on the order of 71.84 newtons. So in order of magnitude, we see that this is the largest, right? F2 has 100 newtons of force directed along it. Next is going to be F2. And then the last is going to be F3. So strongest, second strongest, weakest. Okay, but this is more or less just a problem in understanding what it means to be in equilibrium, how to work out the components in the E1 and E2 directions, and then how to use the equilibrium condition to solve for the unknown magnitudes. In this case, the length of F1, F2 and the length of F3. Okay, so I hope that was a satisfactory explanation for you. That draws a conclusion to this section 1.4, so I will see you again in our next video lecture when we take up our first section of chapter 2. Until then, take care. Bye-bye.